So we've talked about alkanes and alkenes, right? Alkanes are all single bonds in hydrocarbons, and alkenes are hydrocarbons that have a double bond in them. Now we're going to look at alkynes. Okay, so alkynes are going to have a triple bond. And so the alkynes we're going to start with, we're going to look at initially C2H4, which has a common name called acetylene. Okay, the IUPAC name would be ethine. Okay. Oh, that's why did I put an extra E in there? I don't know why I put an extra E in there, but I did. Ooh, come on, there we go. YNE. There we go. So basically, if you have the Lewis structure for this, right, it's going to be H bonded to C with a triple bond to another carbon with a hydrogen there. And so if we look at these, the bonding in this, we've got a single bond, right? So there's a sigma bond there, and there's a sigma bond there. Those are essentially equivalent, right? Where you have a carbon sp hybrid orbital bonded to a hydrogen 1s, and this bond here, right, has the two carbons, and so this is a triple bond. So you have a sigma bond, you have a pi bond, and another pi bond, where both of the carbons there are sp hybridized, so they're going to be carbon sp to carbon sp. Clean that up a little bit. All right. And your pi bonds are going to be carbon 2p orbitals. So you can say 2px or 2py, doesn't really matter which ones you choose as long as they're the same. And the other one will be a carbon 2py. Oop. Okay. This should be a 2. There we go. 2py to carbon 2py. And so that's the bonding in acetylene. And so what we're going to really get to with alkynes is this is just the simplest of the alkynes out there. All the other alkynes that we're going to see have at least one more carbon. So we'll have hydrogen bonded to a carbon, bonded to another carbon, bonded to, say, a third carbon. And so this one would be, well, it's 3 carbons long, so propyne. Okay. And keep in mind that you have that angle there, right? That's a 180-degree bond angle there, and there's a 180-degree bond angle there, okay, in both of those cases. If you have a 4-carbon chain with a triple bond in there. So if propyne is C3H4, you could look at having 2 versions of the C4H6 molecule, okay, 2 versions of this butane. And so one of them would be with the triple bond between the first and second carbons. Okay, so that would be 1 butane. Okay, or you could have it in between the second and the third. H3, C bonded to a C, triple bond, C bonded to CH3. Right, and so that one would be 2 butane. Right, in this case, you don't have to worry about cis-trans isomers because that bond angle here and here, right, since those are both 180 degrees, you don't have to worry about cis-trans isomerism when it comes to alkynes. But you do have to specify where they're at in the molecule. Okay, so hopefully that's nice and straightforward. And so if you have, for example, something like this, right, where you have the triple bond is on the end. So here's CH2, CH2, CH3. So this would be there's 1, 2, 3, 4, 5 carbons, so 1 pentyne. Okay, so all of these, okay, all of these are examples of a terminal alkyne. Okay, so terminal just says that the triple bond is on the end, basically. It's between the first and second carbons. And so that's something that's going to be kind of important, because when you have a terminal alkyne, that proton in a terminal alkyne is of higher acidity than a lot of other carbon or hydrogens on carbons, right? Okay, so it just turns out that is a slightly more acidic hydrogen. In other words, it dissociates a little bit more easily, right? So it has a lower pKa, right, or a higher Ka, which is kind of an interesting thing that you might encounter in chem, in like an organic chem class. We're not going to dive into it any deeper than that right now, but that has implications for chemical reactions of some alkynes. And so now we have alkanes, alkenes, and alkynes, and I've actually done some nomenclature on it. So the first thing is when you have an alkane, right, to an alkyne, right? So this is going to be single bonds, right, which we know from the ending there, and the YNE ending says that you have at least one triple bond. Okay. And we're going to also specify the position just like we did before. Like we did in an alkyne, like we did in an alkene. Okay, and again, there's no cis-trans isomerism. Okay, so it's really the same type of naming that you get with alkenes, except for this time you don't have to worry about the cis-trans isomerism. It's pretty much as simple as that. And so ways we can do that. So let's pull up. Let's see. How about let's do a new one. So we'll do this with line angle drawing. We'll do a new example. So your triple bond is going to look something like that. You could put a hydrogen in on the end of it. You don't need to, but then you would start doing angles after that. So you'd actually, in your line angle drawing, you would actually depict this as either a 180 degrees, or you don't even have to depict that carbon on there, right? But you would essentially have, it did not connect that. This is the same molecule, right? Just in one case, I depicted the hydrogen. Sometimes you might want to do, if you're expressing it as an acidic hydrogen, but you don't necessarily need to do that, because we know that carbon on the end there is attached to one hydrogen, because the carbon forms, that terminal carbon forms 4 bonds, right? Okay. So in these cases, right, this is a line angle formula. So again, this has 1, 2, 3, 4, 5, 6. So this is an example of either 1 hexyne or hex -1 -yne. And that might be more important if you have like a bunch of other things bonded to this carbon chain. So you can do it either way, and it's really an acceptable way of writing that name, okay? Or if you have something like and sometimes I don't attach these well because I try to make it seem like it makes some sense. So 1, 2, 3, 4, 5, 6. And so this would be 3-hexyne or hex 3-ine. Okay, either way that works. So again, naming is similar to what you do in the alkenes. Okay. When it comes to reactions of alkenes and alkynes, really the most common ones that you're going to see are hydrogenation, right? The reverse, if you will, of dehydrogenation that we saw for alkanes. And so the way this works is you have the alkene or the alkyne will react with hydrogen gas to form the alkane. And this takes place using a catalyst. Usually you have some sort of like a platinum or palladium solid metal catalyst that does this. And the catalyst tends to basically attach it, or in this case, this is propyne, right? What happens is the propyne basically attaches to the platinum surface and that adjusts the energy of the orbitals such that it lowers the energy and makes it, and at the same time, the hydrogen is going to kind of stick to the platinum as well. And so it actually brings the hydrogen sort of in proximity to the rest of the molecule so that the hydrogen can, what we call add, so H2 adds across the double or triple bond. Okay. In a halogenation, it's the same type of an idea, and these are both examples of addition reactions, but it's the same idea. In this case, the bromine, so Br2, is going to add, or chlorine or fluorine will work in kind of the same way. Will add across the double bond or triple bond. Right, so in the case of what we have here, right, it may be actually easier to visualize the product here as having now a bromine there and a bromine there, okay? And so that's the idea with these, what are called addition reactions. So when we looked at the alkanes, with the alkanes we had substitution reactions and we had elimination reactions. With hydrogenation reactions and halogenation for alkenes and alkynes, we'd have additions. And so that's going to be an important thing when you go on to organic chemistry, is you're going to have those three categories of reactions, right? You're going to have elimination, substitution, and addition reactions, and those are going to be the important ones that you're going to see. Some other ones that you'll see are like dehydration reactions as well. But there are a few sort of types of reactions that you'll see over and over again, right? So now that we've covered all the different categories of alkanes, we're going to go to and alkenes and alkynes. We're going to go to a very specific type of substance, which is an aromatic hydrocarbon. They get the name aromatic because they're often found in things that you smell. They're things that are aromatic. And they have this structure that is similar to what benzene has. Okay, so benzene is sort of the most common of the aromatic hydrocarbons from the standpoint of the structure of benzene is found across the board in many, many, many compounds. Now, just to remind you, things that you did way back in chapter 9 of Chem 101, as you were looking at bonding, we looked at the hybrid orbital theory, and we said, okay, well, in a benzene molecule, remember a benzene molecule, hopefully you remember from then, right, looks something like this. And it has resonance. Draw my double bonds in there. Right, so it looks something like that. Of course, now that we know line angle drawings, we can draw out benzene like so. A lot easier to do. Right, so there's a benzene molecule, and when we look at this, right, we know that there's this pi system and that benzene has resonance. And since benzene has resonance, we can draw it out like this as well. And understand that the actual structure of benzene is a superposition, right, of these two structures. Okay, so that's this. But what we do know is that each of the carbons are held together with a sigma bond between each of those carbon atoms, right? And that's what's depicted here is these sigma bonds. And you can think of each of these sigma bonds as being its own bonding axis. But on top of that, we have the p orbitals that are perpendicular to each of the atoms. So there's a p orbital vertically there, or there, or there, right? Or there, or there, or there. And those p orbitals can form a pi system that goes around the entire ring, and that's what's described over on the right side. And what you have here are the what are considered the bonding and anti-bonding orbitals associated with the overlap of the p orbitals from all 6 of the carbon atoms. So the most stable, the lowest energy of those orbitals is where they're all in the same phase. The next most stable is where you have one node, and there are 2 ways that you can have one node in this particular molecule. There's like that, and then there's like that. And these are coming from some simulations and things that we don't need to dive into here. You'll talk a little bit more about in an organic chemistry class. If you go to the next, most stable, you'll have 2 nodes, and these are where we start to consider these to be anti-bonding orbitals, where you have 2 nodes for these molecules. And then the highest energy is where you have nodes essentially between every one of those p orbitals. And so what we can kind of think about when we think about the bonding within a benzene molecule, we kind of a lot of times sort of shorten our understanding to this the example on the bottom, where you have orbital overlap between the p orbitals for all of them, where they're all in phase. And that leads to sort of 2 rings of electron density above the plane of the carbon atoms, which is another important part to this, is that the carbon atoms all lie in the same plane, right? These are all trigonal planar carbons. And so if they're all trigonal planar and they include at least 3 carbons, then the whole thing is going to lie in the plane, okay? And so aromatic hydrocarbons, they're very common. They tend to be somewhat relatively stable molecules. Benzene's a pretty stable molecule. And they act a little differently than your typical alkene, even though it's double bonds, right? There are 3 double bonds, if you will, in this particular molecule, and they're all what are called conjugated, right? So when we've looked at double bonds in the past, we talked a little bit about this back in Chem 101, but the CC double bonds are conjugated, right? Essentially showing, leading to this property whereby we can consider all of those p orbitals to be in the same phase and give you one big old pi system, right? So that this would be a pi bonding system. Okay. Now, benzene is one of this class of organic molecules that are called aromatic, and they all have this relationship where they have a certain number of these pi, double bond, single bond, double bond motifs that is repeating in some way. But the key here is this is a sort of a scaffold for a lot of other important compounds in organic chemistry. Now, one of the things about benzene that's very different from the typical alkenes is that reactions of benzene, the benzene doesn't undergo addition reactions, and that's kind of an important thing. because then you can make all kinds of different substances. So for example, if you wanted to have a reaction of benzene with chlorine in the presence of a catalyst, okay, you would actually add the chlorine atom, or substitute the chlorine atom for one of the hydrogens. So you would make essentially something that looks like this. Oh, and I totally was doing thinking two things at one time while I was trying to write this. I want to go back and touch on something before I finish that drawing. And that's this. This piece here, I want to take a second and show you something that we can do with benzene. So we can depict benzene because it exists as that superposition of those two structures. We can actually draw benzene out. Instead of having to draw all the double bonds, we can actually just draw it with a little circle in there. That's sort of the superposition. This is the resonance hybrid structure, okay? And so that's something we'll often do with benzene, okay? Is we'll draw it out. Instead of drawing all the double bonds in, we'll just draw the circle saying, oh, well, it can exist as the superposition of those two resonance structures. And so that's what I'll do here, is we'll just do this in there, showing the addition of, or excuse me, the substitution of a chlorine for one of the protons or the hydrogens on the benzene. Now, this type of addition does affect if you want to do it a second time, but we're not going to get into subsequent additions to a benzene atom. This molecule will then be called chlorobenzene. Okay, so you're adding the chlorine to the benzene, and then now you have a functional group. And you don't need to number this for this particular substance, because there's only one on there, and it's a cyclic structure. You can also add or have a reaction of benzene with nitric acid in the presence of sulfuric acid, and that actually adds a what's called, or substitutes, a nitro group. Okay, so a nitro group is a functional group, right? It's a group of atoms that has some measure of functionality to it, and that would produce a nitrobenzene. Again, you can draw out the structure. And if we wanted to, so we can worry about that later. We're going to see nitrobenzene is actually going to be something we can talk about a little bit if we have time, a little bit later if we get to to a compound with more substituents than just the nitro group on it. But the NO2, anytime you see an NO2, that is a nitro group, and so it's bonded to the benzene ring through the nitrogen. Okay. Another thing you can do is actually do a substitution reaction where you have something like chloromethane, and the chloromethane will actually substitute a methyl group onto the benzene ring. Okay, and so that'll give you a structure like this. So it's kind of like, if you will, a methyl benzene. Okay, but actually it has a common name that we use all the time, and that is actually, as you can see here, toluene, which you guys have actually used toluene. If you think back to the physical properties lab way at the beginning of Chem 101, you were identifying physical properties and solubility using toluene, okay? And so this is a chemical compound that is another very common one in organic chemistry. So you'll see that somewhat regularly in many chemical reactions. Okay. All right. Now, if you have more than one substituent on the benzene ring, for example, so if I have two substituents on the benzene ring, oops, that did not work. Try that again. Try drawing a hexagon rather than a pentagon. There we go. So if you have a benzene ring and you have two things bonded to it, we're going to call that either R. So remember, R is just a hydrocarbon of some kind, and R prime, which just says a different hydrocarbon. Or you could say X or X prime if you want to make them into halogens and that kind of thing. But if you look at those two positions, okay, we can say, well, here's our 1 position, right, our 2 position, 3, 4, 5, and 6, okay? And there's the priority there is something we can worry about later, but the key for naming here is if those substances, those substituents are at the 1 and 2 position, those substituents are ortho to each other. Okay, so if you were to have something like a dichlorobenzene, so we'll put a chlorine and another chlorine, those 2 chlorines are going to be ortho to each other, and so it would be ortho, okay, dichlorobenzene. Okay. Also, or you could just put it with the little O, dichlorobenzene. Right? Or 1,2-dichlorobenzene. And so what this is doing now is you have these prefixes that will tell you in what relationship are the substituents to each other on that benzene ring. So if you were to have them at the 1 and 3 positions, right? 1, 2, 3. Okay, then you would have meta, okay, as your prefix. Okay, so an example, maybe we can do something like bromine. So this would be meta dibromobenzene. Okay, or little m dash dibromobenzene. Or 1,3 dibromobenzene. Okay. Or if you have them opposite each other at the 1 and 4 position, so 1, 2, 3, 4, 5, 6, those are at the para positions. Don't need to capitalize that. So at the para position, so we'll do this. Right, so this would be para diiodobenzene. Right, or para p diiodobenzene. Or 1,4 diiodobenzene. Okay, and so those are how we would name various compounds. So we can name them based on numbers, or we can name them using prefixes. Okay, so those are ortho, meta, and para positions. Okay, if you want a couple little visual organic chemistry puns. All right, so here's this. Some little, like I said, really bad jokes. You know I make them. Here they are. What you have here is you have PhD that is para to an MD. This would be paradox. Good? Yeah, no? Anywho, you knew I was gonna come up with some of those, right? There's some really good ones out there for this too, and you can be creative with this as well. Go back a second. I'll give you one more, which is kind of fun. We'll do 2 medical doctors on this one. Oop, MD, that should be capitalized. D. So another name for a medical doctor is a physician. So this would be a metaphysician. Right? Anyway, you can name these things, have some fun with the names. There's all kinds of good ones out there, and using, say, benzenes, ortho-meta para positions, or even the cis-trans isomers from the alkenes as well. But there is one other chemical compound that I want you to see and know. I think it's a fun one, mostly because we've all heard of this one before. And so we've been introduced to the molecules and the substituents enough. So this is going to start out with a toluene molecule, and I'm going to put a bunch of nitro groups on it. Okay, so this particular molecule is going to actually have the name of, what is it? 2,4,6-tri-nitrotoluene, which, if you are familiar with it, the tri-nitrotoluene, another name for T in T. Right, so that's what a trinitrotoluene molecule is, which you, of course, if you've ever seen Wile E. Coyote and the Roadrunner, right? It's fairly common in their dynamite to have them labeled with TNT. So that's the actual chemical compound. And the reason that that is a chemical compound that is explosive has to do with how this molecule is formed and the stability of the benzene molecule when you have those nitro groups. So something that's interesting about the substituents on a benzene is the nature of the substituents has a significant impact on the stability of the molecule. And nitro groups make that toluene molecule much, much less stable. Okay. The other thing you'll see is a benzene as a substituent. For example, you could have some long molecule like this, and you could have a benzene coming off of it. When that's the case, when you have sort of a benzene as a substituent, we call that a phenyl group or a phenyl substituent. Okay, and so on this one, you could imagine counting, right? 1, 2, 3, 4, 5, 6, and you could say that this would be 2-phenyl hexane, right? So occasionally you'll get these as substituents on larger things, and so that's where the name, what you'll find is that has a name, phenyl. Okay, it's a phenyl substituent. Okay. So now we've got alkanes and alkenes and alkynes and benzene-based compounds. And so we're really sort of moving on through the nomenclature of a lot of things that you'll see these, for those of you who are going on and taking organic chemistry right away, this should be familiar to you when you get there. It's a little bit less memorizing to do when you get into the organic class. So it's sort of meant to position you well as you go on to organic chemistry. The other thing that I want us to look at today, and we'll probably finish with this page is my guess, and we'll get into more of the nomenclature of these hydrocarbons next time around, is what are called hydrocarbon derivatives. Okay, so hydrocarbon derivatives have a functional group. Okay, a functional group is all it is a group of atoms that lends some sort of functionality to the hydrocarbon to which it's attached. All right, so we've already seen one of these, right? We've seen the halo hydrocarbons, right? The halo hydrocarbons have the functional group is a halogen. All right, so chlorine, fluorine, bromine, iodine, right? Those ones are all the halogens. So we've already done the nomenclature of those, right? Chloromethane, bromomethane, etc., right? So on those, we're just dropping the INE, right? Ending, and we replace it with -O, right? So that was what we did there. Now with alcohols, and we're going to get, like I said, we're going to get into the nomenclature later. With alcohols, we have this, the key is the OH. Now, when we talk about alcohols, keep in mind, and this is something we talked about back in 101, because I tried to stress it quite a bit. So if you were to have, say, methanol, CH3OH, remember that bond right there? That is a covalent bond. Okay? So it's not a hydroxide, right? It's not a hydroxide ion. Right? It's covalent, so it's not going to dissociate. In fact, if anything dissociates here, that proton on there might break off a little bit. It's somewhat acidic, but it's very weakly acidic. Okay, and so that's going to be, and you can think about it this way based on some of the acid-base chemistry that we looked at. When we had, for example, the amines, we looked at how the basicity of the amine. For example, if you go from ammonia to a methylamine, right? The methylamine was more basic because that methyl group is somewhat electron donating overall to this, and so it makes the bond between the oxygen and the hydrogen stronger, if you will. And so that's one of the keys there. It's not going to be very acidic, but it does have some acidity to it. When you have an ether, right? The functional group on the ether is you have two organic pieces or two hydrocarbon-based pieces that are attached to each other through bonds to an oxygen, right? Now, keep in mind, if we're really thinking about Lewis structures, you'll notice a lot of these Lewis structures don't include the lone pairs of electrons. So when you think about the structure here, right, this is actually going to be a bent structure, right? Which you know because you did Chem 101 and you know how to complete Lewis structures, and when the oxygen actually has an octet, right, it's going to have a tetrahedral structure where there's two lone pairs that are causing that to be bent. Okay. When it comes to an aldehyde, so an aldehyde, and actually really the next four that we're going to look at have this one thing in common. What they have in common is this C double bond O, right, and then the carbon that's double bonded to the oxygen is bonded to other things. That C double bond O has a certain name that you'll run into. It's called a carbonyl. Okay, and it's part of each of those functional groups. Okay, so the aldehyde functional group, do that over here. So it's R. If we do the Lewis structure of it, we've got the carbon, where the carbon is double bonded to the oxygen, which is bonded to a hydrogen. Now, something that these all have in common, when they have this carbonyl, we're going to talk a little bit about this in terms of key properties of the carbonyl once we have all of these down in just a moment. So that's an aldehyde, and aldehydes are different from ketones in a small way. Instead of having the hydrogen on the other side of the carbonyl, there's another hydrocarbon on the other side of the carbonyl. So that's where that R comes from. So the C double bond is in that way. And so you can also look at the angles around here, right? You have each of these are going to be trigonal planar molecules, at least maybe slightly distorted, but trigonal planar overall as the ideal bond angle. When you have a carboxylic acid, now you have an R, some sort of an organic part bonded to a carbonyl, and on the other side of the carbonyl is an OH. Now this one is an acid because, well, now you have the C double bond O, right, is that oxygen is electron withdrawing, right? So that's pulling electrons away, it's electronegative. And so it forces the bond between the hydrogen and the oxygen to be a little bit weaker through the inductive effect, right? But there's only one proton and two oxygen, so there's only one more oxygen than ionizable proton. So these are all going to fall under the weak acid category, unless there's something else going on that could possibly make it a stronger acid. And then the other category here is sort of related to the carboxylic acids. You have R, so the organic group, bonded to a carbon, or bonded to a carbonyl, the carbonyl carbon. And on the other side of that is an oxygen. Instead of a hydrogen, now you have the another hydrocarbon group. So you basically are we're sort of progressing through the complexity of these things. And these compounds have different functionalities. For example, esters tend to be very fragrant compounds. So the sour apple smell, if you've ever had like sour caramel apple pops, that sour apple smell comes from an ester. The banana smell, that synthetic banana smell, comes from an ester. There's all kinds of substances that have interesting flavor and aroma compounds that come from esters. The sort of the thing that ties these together, though, is this property with the carbonyl. So the carbonyl has this basic structure, right, where you've got the carbon double bonded to an oxygen, and there's other things on the other side. But the big key here, they're going to all have some measure of similar reactivities. And this is sort of, I want to bring back something that we haven't talked about a lot in this semester, but we talked about a lot in Chem 101, is the nature of chemistry. What the secret to chemistry, right, is all about charges. So chemical reactions are going to occur a lot here with these carbonyl groups because of the nature of oxygen being much more electronegative than carbon, right? And so what's going to happen is that the oxygen is going to have a big old partial negative on it, and the carbon is going to have a big old partial positive, which is going to facilitate reactions from things that are basic, or what are called nucleophiles, that'll come in and start a reaction by reacting with that carbon first, and that's going to precipitate a larger reaction on the whole. But the reason I bring this up now with these functional groups is because it's sort of the first big application of how the charges are really, really important in an organic chemistry framework, right? It's all about electronegativities. I had a friend in grad school who told me, oh, organic chemistry is all about electronegativities. And I really, really wish that my professor in grad school had told me that, because when this person said that, I was just like, oh, boom, this light bulb went off in my head and made organic chemistry so much easier. So if you think about organic chemistry, especially the reaction standpoint of organic chemistry, understanding electronegativities is of the utmost importance. And so that all four of those types of functional groups have this carbonyl carbon oxygen functional group within them. And so that'll have implications for the reactivity later on. Finally, the last group that we'll talk about are amines. And so amines just have this NH2 in them. So if you remember talking about amino acids, right? Amino acids have this NH2, okay? So R bonded to an N, the nitrogen will have a lone pair of electrons on it. They'll each be bonded to a hydrogen. And so amines tend to be basic compounds. They also tend to smell pretty bad too with how they interact with your olfactory senses. I remember the first time I did any research, I asked my organic chemistry professor, who was gracious enough to allow me to do research in his lab. And the first thing we ever did, we went and did a chemical reaction, and he pulled out isopropylamine, which has this formula to it. And he said to me, this is isopropylamine. It is, it smells really bad. We're going to keep it in the fume hood because it's a main component of rat pee, which is like, oh, okay. So we mixed that with something else and made a new compound from it because of the reactivity with one of the things that we were interested in. Anyway, things like amines tend to be very strong smelling. And you know, if you really want to be disliked among a group of people, you walk down the hallway with an open container of amines or thiols, and people will really dislike you for it because they smell really, really bad. Anyway, we're going to stop right there, and we'll pick up with some more organic chemistry on Monday. So let's stop that recording.